Hi everyone, Mr. Boltri here, bringing you video 5.9. We're going to talk about angular momentum. To do that, we're going to review linear momentum, talk about the angular momentum of a system of particles, and also for a rigid body, and then talk about the idea of conservation of angular momentum. So reviewing what we know about linear momentum, first, momentum, it can be found by taking the mass and multiplying by the velocity. And these are vectors, so the direction is important. We also know that Newton derived his second law, the FAM law, by using momentum and saying the net force equals the derivative of momentum with respect to time. And we showed that this, since momentum is mass times velocity and the derivative of velocity with respect to time is acceleration, we showed that this equals mass times acceleration, assuming a constant mass. But if we don't have a constant mass, then we can just use the product rule on this bad boy. And then also we talked about how impulse is the change in momentum and can be found by taking the area of a force versus time graph or integrating the force function with respect to time. And this allowed us to derive the idea of conservation of linear momentum, because if there's no external forces or the net force is zero, then there's going to be no change in momentum. So the final momentum is going to equal the initial momentum. So this is important because if we draw our system wide enough such that there are no external forces, and that means that the momentum is not going to change. So it may be transferred from one object to another or become positive or become negative, but overall, there's going to be no net change in momentum. So this is a really important and powerful tool and often used to solve collision problems. So now let's talk about the angular momentum of a particle. In the angular momentum of a particle, angular momentum is going to be represented by the symbol L, which is kind of annoying because we've also been using L to talk about length, but it is what it is. So L, the symbol L for angular momentum of a particle, can be found by taking the position of that particle with respect to the axis of rotation and multiplying it by the linear momentum of that particle. So R, the distance from the axis of rotation, times mv, or cross product mv. So the cross product there is important because we can then use the right-hand rule to tell us the direction of the angular momentum. Or if we wanted to find the magnitude of the angular momentum, we could do r times mass times velocity times the sine of the angle between these two vectors. That would give us the magnitude. Or we could do the cross product to give us the magnitude and the direction using the right-hand rule. So if we take these, so this is the angular momentum for one particle. And so then if we want to find the angular momentum of a system, a bunch of particles all together, it's going to be capital L is going to be take all of the little angular momentums of all the little point particles and add them together. Or if we wanted to find the angular momentum of a body, we could do this, but with an infinite number of little point particle angular momentums. And then that would give us the integral of all of these added up with a bunch of minuscule masses. And then if we do that, then we're going to get that the angular momentum of a body equals the moment of inertia of that body times the angular velocity. And just like before with Newton's second law, we can say that the net torque, which is angular force, is going to equal the derivative of the angular momentum with respect to time. And also, there is not a symbol for angular impulse, unfortunately, but the idea of angular impulse is still there in that the area of the torque with respect to time graph is going to equal the change in angular momentum, or we could call that the angular impulse if we wanted to. And we can come up with a symbol for that if we want to, but as far as the AP exam is concerned, delta L is angular impulse, the change in the angular momentum. So now let's compare the linear momentum versus the angular momentum. And hopefully you see a lot of patterns here. Again, so we have linear, angular. So linear mass, linear velocity, angular velocity. Linear momentum, angular momentum, a linear force, angular force. So it's so similar to what we've been doing, which is weird because it feels so different, but it is so similar to what we've been doing that this should just be a refresher and an add-on on top of kind of the ideas that we've already been learning about momentum. And speaking of ideas that we've already been learning about momentum, let's talk about conservation of angular momentum. So like we said before, if the net torque on the system is zero, which would make sense if there's no external torques, no external forces. All of the torques and all of the forces are internal to our system. Then there's going to be no change in our angular momentum. So if the net torque is zero, then the change in angular momentum is going to be zero. which most often comes up in problems by saying that the angular momentum at the beginning is going to equal the angular momentum at the end. And this is a simplified version. And the biggest thing that I've simplified about this is there's an implied sine of 90 degrees in here, sine of 90 degrees over here. So it might be better to write sine of theta, but the angular momentum at the beginning is going to equal the angular momentum at the end. And it could be two particles added together or just the beginning and the end. So this is going to be Mr. Boltri wrapping up video 5.9. We're going to do some practice problems for angular momentum in our next class. But for now, go Bears.